prove that the integral part of alpha to the power of n is divisible by k. Alpha equals k plus a half plus root of k squared plus a quarter. K is a positive integer for all n in the set of positive integers. X equals minus b plus minus root of b squared minus 4ac over 2a are roots of the quadratic equation ax squared plus bx plus c equals 0. Alpha equals k plus a half plus root of k squared plus a quarter must be a root of a quadratic equation. To find the quadratic equation, we rearrange alpha, so alpha can be written as 2k plus 1 plus 2 times root of k squared plus a quarter over 2 equals 2k plus 1 plus root of 4k squared plus 1 over 2. And write 4k squared plus 1 as 2k plus 1 all squared minus 4k. Thus, alpha is a root of x squared minus 2k plus 1 times x plus k equals 0. Beta equals k plus a half minus root of k squared plus a quarter is another root of equation 1. Since k plus a half all squared equals k squared plus a quarter plus k. K is a positive integer, so k squared plus a quarter is less than k plus a half all to the power of 2, which means root of k squared plus a quarter is less than k plus a half. Thus, beta is greater than 0. By Vieta's formulas, we know that alpha beta equals k. By rearranging the equation, beta equals k over alpha, which is equal to k over k plus a half plus root of k squared plus a quarter, which is less than 1. Thus, for all n in the set of positive integers, 0 is less than beta to the power of n is less than 1. Let un equal alpha to the power of n plus beta to the power of n. We have un minus 1 is less than alpha to the power of n is less than un. If un is an integer, then the integral parts of alpha to the power of n equals un minus 1. Thus, proving that the integral parts of alpha to the power of n is divisible by k is equivalent to proving that un is an integer and un is congruent to 1 mod k. Since alpha and beta are the roots of equation 1, so alpha squared minus 2k plus 1 times alpha plus k equals 0. Beta squared minus 2k plus 1 times beta plus k equals 0. Multiplying both sides of equation 2 by alpha to the power of n, we have alpha to the power of n plus 2 minus 2k plus 1 times alpha to the power of n plus 1 plus k alpha to the power of n equals 0. Multiplying both sides of equation 3 by beta to the power of n, we have beta to the power of n plus 2 minus 2k plus 1 times beta to the power of n plus 1 plus k beta to the power of n equals 0. Equation 4 plus equation 5, we have alpha to the power of n plus 2 plus beta to the power of n plus 2 minus 2k plus 1 times alpha to the power of n plus 1 plus beta to the power of n plus 1 plus k times alpha to the power of n plus beta to the power of n equals 0. Alpha to the power of n plus 2 plus beta to the power of n plus 2 equals un plus 2. Alpha to the power of n plus 1 plus beta to the power of n plus 1 equals un plus 1. Alpha to the power of n plus beta to the power of n equals un. By rearranging the equation, we have un plus 2 equals 2k plus 1 times un plus 1 minus kun. Un plus 2 can be written as k times 2un plus 1 minus un plus 1. Base case, n equals 1, u1 equals alpha plus beta, which is equal to k plus a half plus root of k squared plus a quarter plus k plus a half minus root of k squared plus a quarter equals 2k plus 1. Thus, u1 is an integer and u1 is congruent to 1 mod k. N equals 2, u2 equals alpha squared plus beta squared equals k plus a half plus root of k squared plus a quarter all squared plus k plus a half minus root of k squared plus a quarter all squared, which is equal to 2 times k plus a half all squared plus 2 times root of k squared plus a quarter all squared, which is equal to 2 times k squared plus k plus a quarter plus 2 times k squared plus a quarter, which can be simplified to 4k squared plus 2k plus 1. Thus, u2 is an integer and u2 is congruent to 1 mod k. Induction step. Assume that for all m in the set of positive integers um and plus 1 are integers and is congruent to 1 mod k, plus 1 is congruent to 1 mod k. From equation 6, we have plus 2 equals k times 2 plus 1 minus plus plus 1. Since k is a positive integer, and plus 1 are integers, so plus 2 is an integer. Plus 1 is congruent to 1 mod k, so plus 2 is congruent to 1 mod k. Thus, un for all n in the set of positive integers is an integer and is congruent to 1 mod k. Hence, the integral parts of alpha to the power of n for all n in the set of positive integers is divisible by k. The proof is now complete. Thank you for watching. Hope you found this video helpful. Please subscribe to this YouTube channel for notification of new videos. See you next time.